This is 2020 AIME II problem number 14, and here is a view of this algebra combo problem. The statement of the problem is, I guess, clear, right? So we have a function defined as such: f of x equals x times the fractional part of x, and there's also a definition for that as well. And given that, we want to find the number of solutions to this equation in the given interval between 0 and 2020. All right, so before we go into the composition here, composing f onto itself 3 times, we need to first make sure we understand how to draw f of x. All right, so let's go ahead with that. As you can see, f of x is just the product of x with the fractional part of x. So what I will do is I will just go ahead and create this very simple sketch, hopefully just to make sense of it, and then I will yet construct a second sketch just for the composition business. All right, so we have x here. Well, the first part is pretty easy. F of x equals x is just a 45-degree line. There you go. So this is so the first part, if you will, y equals x line, or you can call it y1 equals x. And then for the fractional part, and probably in my YouTube channel we've seen this a lot. I remember a few years ago there was this AIME 10 problem. But so what we do is, so this is 1. So this is 1. So between 0 and 1, the fractional part of a number, based on, if you read these explanations, I think it's clear that it is the difference between the original number and the floor of that number. So which is, so the difference is the fractional part. So the fractional part of x itself would be the following. And let me go ahead and draw it with red color. So it would be starting from 0. We will go all the way up to 1, but just shy of 1. And then we make a jump, right? And then, so this is 1, obviously. We go all the way up to 2 again, except we are shy of 2, and so on. That's the value that 2 takes, and so on. I think it's very straightforward how we draw this, the fractional part function. And well, now that we have the understanding of the fractional part and the first part and the second part, so this function we can call it y2, which is equal to the fractional part of x, where x is the horizontal axis. Now we can go ahead and multiply them out. So multiply the blue function and the red function. Let me go ahead and use black color this time, or maybe green. Okay, we haven't used green yet. I think it's very straightforward what happens in the interval 0, 1. The red times, well, actually, even there it's not clear. Well, okay, so for instance, both of them takes the value 1/2. 1/2 times 1/2 is 1/4. So I think it's something like, this is closed, and then so something like that, I would guess. Do you guys agree? Except we're just shy of this point. At that point, we jump back to 1. I mean, at x equals 1, we jump back to 0. But then something strange happens. So we are going to multiply all these red values with all these blue values between the interval 1 and 2. Whenever x is between 1 and 2. And I think it's clear that you will end up with a function which will look like this. It will clearly be, except it's shy of this point. It will clearly be an increasing function. You can use some analytical techniques if you want to, but I think it's clear that within the interval 1, 2, when I say 1, 2, 1 included and 2 excluded, the function f of x is clearly continuous. And the first component is increasing, the second component is increasing. It has to be an increasing function, right? So, all right. And then we make a jump. We go back to, at x equals 2, we go back to y equals 0. And then we go all the way up to, okay, first let's identify that point. There you go, just shy of that point. And then we make a jump again. Do you guys see that, huh? So this is just a piecewise defined function. There you go, and so on. Now that we have a more or less a reasonable understanding of our function f of x, now let's just attempt to understand f of x equals 17. Let's figure out how many solutions, real solutions, by the way, real solutions to that composition function. So let me go ahead and draw yet a new picture so that we can make sense of all that. Okay, so I have enough space there. It will be a big picture, obviously. It's the AIME. We knew this would be bashy and stuff. The y-axis here. We have the 45-degree line. Actually, let me go ahead and draw. So this is the 45-degree line, light blue color again. And now the critical thing, huh? f of x, 1, 2, 3, equals 17. So we need to investigate that. We already know how the function will look like. We just identify where the point 17 is located. I don't know, let's put it somewhere here, I guess. Remember that this is the 45-degree line. So so that's a 17, just for the record. So if I put okay, this is not up to scale, right? So let me put this the traditional not up to scale sign, right? On both ends, actually. Okay, so it's not scale, but so we have 16 here, 15 here, and so on. So our function looks like this. The green function looks like this. So actually, let's first go ahead and draw the perpendicular lines. 18 here, dot, 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 dot. All right, so the green function, the f of x, the function in a sense, huh? So that function is over here. I don't care about, it's not a straight line, I know that. The green thing is not a straight, but I don't care. I know that it's monotonically increasing, and that's what matters. All right, so it's again something similar here. And then finally, the interesting part, we will get this as well. And we will get this throughout the end, right? So in the end, I think the interval of interest was up to 2020. Let me go check. Yes, between x is between 0 and 2020. So 2020 there. And I want to mark our limit here. Okay, so that's our limiting point. Okay, there you go, something like that. 2020. All right, so now we want to see, starting from, so what should be this value? If you call this value, say, for instance, R, or because we have three F's back to back, why don't I just call it R1? All right, so what are the values that R1 can take? Well, if F of something, right, so this whole thing is something which we decided to call it R1, so let's write it here. F of R1 is equal to 17. What is R1? Well, because this is an open interval at this end, it can't be 17 itself. So we want to see where the green function will hit this line over here, the y equals 17 line, right? Yeah, I think it's straightforward. So, and then we just mark those points. Technically, it can be this point, right? Or any subsequent point after that, right? So let me draw a couple others. Let me also put that 19 line here. Do you guys see that? So it can be any subsequent point after that, and so on. So it can be this point, and so on. So you have how many points? How many potential solutions? So this is 2019. Let's put that dotted line here again. And then we have this function our f of x function, which will look like this in the remaining interval between 2019 and 2020. And this is the very last potential solution for R1. So R1 will be one of them. The value that will of f, so which will make, sorry, the value for which, if we apply the function f, it will give us a 17, right? So any one of these black dotted points is an R1. And so let's go ahead and, without loss of generality, let's assume that we are interested in one of those intervals. So pretend that's the interval of interest. We have the portion here. There you go. And this is the R1 that we want to pick. All right, so we can pick any R1. The question is asking how many solutions. But first, let's build at least one solution so that we understand the logic behind it. So if this is R1, right, then what? Then we are in the second step. Because R1 is this inside of this, which makes it equal to 17. So f of x better be equal to R1 will be the next step, right? So that's the next step we want to solve. All right, so let's write that down. Now we are on to f of x is equal to R1. Well, where is the value of R1? So I know R1 is here, but wait a second. This blue line was which I just deleted. This was the 45-degree line, right? All I do is you go back all the way up, back to the line, 45-degree line, and boom. So that's the value of interest for us. That's R1. Do you guys see that? And let me go ahead and draw a light green line here this time. And yes, perfect. So do you guys now, I think we agree that what are the potential solutions for, if you call this one now R2, so f of R2 is equal to R1, right? So I want to figure out what are the potential solutions for R2. So far I realized that R1 can be anything between 17 and 18, or, well, sorry, R1 is one of these points, right? So one of these black points. We didn't even bother counting it, right? So, but the counting, I will do it in the end. But clearly R1 has got to be greater than 17. It can't be 17 because this one was open. Do you guys see that? So all of these are closed. All right, so maybe I just messed up my own drawing. I do that all the time. Oh gosh, okay, so let's go back. All right, I don't want those to look like they are open intervals. They are not. Okay, there you go. All right, back to our picture, as they would say it in French. My next video would be a Polish 2019 Polish Math Olympiad problem, where we will use Monge's theorem. I was just thinking about, okay, how am I gonna pronounce this word, Monge, right? So I'm sure you guys have heard of this, Monge's theorem, related to three circles and their tangents, how they're collinear. So Monge was a French mathematician, I believe, and the correct pronunciation, I think, is Monge. But I think in the British English language, we call it Monge or Monge or whatever. All right, so now that we know what R1 is, okay, so we do the same business. Okay, let's just use a different color. How about red? We haven't used red yet. So this is a potential solution. Well, actually, we need to draw all the, let me draw a couple others. So we didn't even bother. We don't even care what these numbers are, right? So L, this one is L plus 1 in that interval. The next one, this point, is L plus 2, where L is an integer, right? But what we care is within that interval, there will be a point where, well, there's both a potential solution for R1, but then within that same interval, you can also get a potential solution for R2 as well, all the way up to here. Do you guys see that? So all of these black dots are potential values that R1 can take. And now all of these red points are potential values that R2 can take. And we just, again, randomly pick one of them, right? Well, because the question says how many. In the end, I will do the count, but I think it will be straightforward by that time. I mean, by now, probably you guys are thinking, hey, what is this guy doing? I mean, aren't we done already and blah, blah, blah. But yeah, so we're just having fun, right? So, like, I don't know what I'm saying. Okay, so forget about what I'm just saying. So pretend this is m, and this one is m plus 1, two consecutive integers. And we have this portion of the function f between m and m plus 1. And suppose that, without loss of generality, we pick this value for R2. And so you just figure out where that value R2 is between m and m plus 1. And then, because this is the value of R2, so R2 is this value, which makes it equal to R1. So finally, last step, we need to pick an R3. So we're almost done, right? So this whole thing is equal to R2, meaning f of x. We need to find an x which will make it equal to R2. That x, let's call it at x equals R3. Now we need to figure out where R3 is, and now just pretty much the same trick that we did. We go back all the way up to the 45-degree line. Aha! So whatever that value is, that is our R2, and now we can draw our last horizontal line. And within that horizontal line, we will now go ahead and start picking the R3s. How many R3s? Well, unfortunately, my picture is... okay, hold on. Let me just try to... okay, so let me revise my picture. Well, you know what? I can use magic here. There you go. Okay, so let's just get rid of this, make it very tiny. There you go. So do you guys agree that that green line here, this green line and that red line, they will intersect at a point? Let's draw the point. So there's a potential point there. So this point is not important, huh? Well, this is the point how we identified where to stop, and then from there, we went to that axis to figure out where R2 is. But these are the potential points for R3, starting from that point all the way up to here. So all these points are potential for R3 values. And that's it. And obviously you can randomly pick any one of them. And then boom, you go down to figure out where it is. But at this step, we don't need it. So now we are ready to make the count. So how many values of R1, R2, R3 are there? R1, R2, R3 are potential points. They are real valued points. Obviously, they are within those intervals. None of them are integer values. However, we know how to count them. How many potential values for R1, right? R1 can be anything between 17. It can't really be 17. We know that for sure. And 2020, it can't be 2020 either. So R1 is a number between 17 and 2020, but because it can't be all the number, it is one of these black dots. So therefore, how many black dots are there? So do you guys see? So there is one solution, one black dot between 17 and 18, one black dot between 18 and 19, and so on. One black dot between 2019 and 2020. Do you guys see that? So one black dot within each of these intervals. And yeah, so you pick any one of those black dots. However, the important thing is when you go to R2 now, R2 has got to be strictly greater than R1. If you just look at this construction, once we identified our R1, we know where R1 is, we go up until we hit the 45-degree line, and then once we have R1 on the horizontal, we draw that green line, and that's when we get that R2 values. And R2 is clearly to the right of R1. So R2 will be greater than R1. Again, it will be short of 2020. And finally, using the same procedure, we can also say that R3 will also be greater than R2, less than 2020. However, now is the good thing, because this is a counting problem and we have limited options here, let's count how many potential values for R1. It is just the number of intervals between 17 and 2020. When I say intervals of length 1, right? Between 17 and 18, 18 and 19, and so on. So you have one potential value for each of these R1s, and so on for R2 and R3. However, okay, even though R2 is greater than R1, R2 can start within the same interval as R1. Do you guys see that? So for instance, this first red, even though it's to the right of the first, whatever black we chose, the first red, the R2. However, the interesting thing is you can still pick up from the same interval, so that's important. So one quick way to identify them would be the interval where they reside, right? Rather than trying to remain on the picture like this. Now it's the whole point is just to bring them into intervals. And the best way probably to think of these intervals is, I'll call the interval 17 to 18. So this is our first interval. Then 18 to 19, we have a second interval, all the way up to 19 to 20. These are our potential intervals. So starting with, let me write those down now. I think we are pretty good now. R1 can live in any of these intervals. There's one R1 in each interval, right? So it can be in any one of these intervals. So it is it's either 17 to 18. Oops, this side is an open interval, or R1 is in 1819, and so on, right? Do you guys agree? Or dot dot dot, or R1 is in 2019 to 2020. Oh boy. So how many intervals did we say? So intervals starting at 17 and ending at 2019. So the one starting with 16 is the last one missing. So we have 16 intervals missing on the beginning from 2019. So in total we have 2019 minus 16, 2003 intervals, where so 2003 potential values for R1. Do you guys see that? So so if you will, we can do it like this. So first interval, or you can call it interval 1, interval 2, interval 3. Interval 1 is this one, interval 2, and so on. Interval 3, I should say, dot dot dot, and the last interval. So this was the last interval. What did we say? 2003, I think we said. 2003. Where did we find it? 2019 minus 16, the missing ones. Anything interval 1 through 16 are all missing. So that's it. So R1, once we decide where R1 is, suppose here R1, then R2 can be anywhere from I3 all the way up to there. So R1 has so many choices. R2 is R1 through 2030. So wherever R1 is, the interval, and anything above that, R2. And finally, once you choose where R2 is, R3 is, so suppose that you choose R2 somewhere here, then R3 is anywhere where R2 is and beyond, right? R3 all the way up to 2013. Do you guys see that? So therefore, yeah, so the rest is just counting how many ways we can choose them. Instead of calling them intervals like I1, I2, I3, I can call them 1, 2, 3, all the way up to 2003. Choose R1, R2, R3 as from the integers 1, 2, 3, right? So now we have this, in a sense, bijection 1, 2, 3, so on, all the way 4, 2002, 2003. All we do is we will just pick 3 numbers, but they don't have to be distinct. How many ways can we pick 3 numbers? That's pretty much it from among these 2003 numbers. For instance, I can pick dot dot and then dot. So what that means is, so the bijection is R1 is selected from the third interval, R2 is also selected from the third interval, and R3 is selected from the 2002nd interval. That's what it means when I select them. Or so I think, does everyone agree? Well, obviously I cannot hear you guys. Well, don't worry, I've been there, done that, you remember? Like, yeah, I think that's clear at this step, that what the meaning of this. So how many different ways can I choose 3 numbers with repetition allowed? That's it. Once those 3 numbers are chosen, the numbers are ordered like this. R1 is less than or equal to R2, less than or equal to R3, right? So they have to be, so, well, when I say, maybe I can associate with R1's case or something, whatever you call it. So, but the intervals, if you wish, the intervals are ordered in that way. All right, so how many ways can this thing be done? Well, okay, so here there's a couple of different ways. Now this is a combo problem. Well, we can choose, okay, what's the long way and then what is the trick way? The long way is this. We can choose all 3 from the first interval. Well, yeah, that's possible. They will be very squished. R1, R2, R3 will be very, like, R1 will be somewhere between 17 and 18. Well, it can't really be 17, but okay, let's just put it like this. R2 will be greater, R3 will be a greater, and then, yeah, this is definitely possible. It will be very tiny, but, so do you guys agree that if I make the picture large, and then there's this not scaling here, all right, so if you have this, all right, so let's do it like this, 17 here, 18 here, you draw that pink line, starting from here, you have your red function, f of x, there. All right, where is R1, R2, R3? If it is possible, 1, 1, 1 is possible, so here you go. So R1 is this number. Once you choose R1 in this interval, R2 will be, so this is R1 as well because you have the 45-degree line. R2 will be this number. And once you have R2, R3 will be that number. There you go, that's R3. It is possible. All three can be within the very first interval. So all three selected from the first interval. So we can do a case work basically. The largest is R3. What is, so here the case one, so case work. So R3 is selected from, R3 is equal to 1 basically. Or R3 can be equal to 2 and the largest one is 2. Well, how many? Well, it can be 1, 1, 2, or it can be 1, 2, 2, or it can be 2, 2, 2. You guys see that? Or R3 can be, so I'm doing a case work on R3 basically. Let me just shift this down a little bit. There you go. Oh, okay, so get rid of that thing. All right, so there you go. R3 can be selected from the third interval, so which means okay, so which means R1 and R2 can be selected in any one of the first three intervals, as long as they are not going above R3, right? So it could be, R1 could be 1, R2 could be 1, but R3 has got to be 3, right? So how many where the third and 3 is a 3? And it's non-decreasing, obviously. So 1, 1, 3 is possible, 1, 2, 3 is possible, 1, 3, 3 is possible, or 2, 2, 2, 3 is possible, 2, 3, 3 is possible, or 3, 3, 3 is possible. Do you guys see the pattern so far? So one solution in this case, 3 solutions in this case, 6 solutions in that case. Keep going. Okay, oh yeah, I know you know it, right? So come on, don't I mean, don't pretend you don't know it. Okay, so you want me to do it one more time? Okay, I'll do it one more time. R3, sorry, the largest one is a 4. So 1, 1, 4, or it can be 1, 2, 4, 1, 3, 4, 1, 4, 4, or 2, 2, 4, 2, 3, 4. When I write those three numbers, the first one is R1, the second one R2, the interval where R2 belongs, and then the third, yeah. Okay, 2, 4, 4, 3, 3, 4, 3, 4, 4, or 4, 4, 4. Yes, and clearly there is, so 6 there, and then here it is 10. Okay, I think you know what's going on. And we can keep going like this. And the largest case where R3 is in the very last interval. In total, we had 2003 intervals, right? So 2003 intervals. R3 can be 2003. How many? Well, obviously, these are the triangular numbers, right? So, and we know how to count them. This one is 1 times 2 over 2. This one is equal to, okay, let's put an equal sign there. This one is 2 times 3 over 2. This one is 3 times 4 over 2, and so on. So it is really whatever that number plus 1, you multiply them, divide by 2, right? Because the largest one is 2003, we can imagine the total number would be 2003 times, 2004, all divided by 2. Now the question is asking you to add up all these numbers and what? And divide by 1,000 and find the remainder, basically. Can I just shift this a little bit before I ruin my picture, which I don't want to. There you go. All right, so let's just have fun with this picture, move it aside. Okay, there you go. I'm exploring different ways to use it. So I kind of enjoyed this PDF document writer. I forgot the name, but anyhow. Okay, what am I doing here? Oh yeah, so add up all these things. All right, so therefore the answer will be the sum of all these numbers. So the sum of n equals from 1 to 2003, n times n plus 1, all divided by 2, evaluated modulo 1000, because the question clearly says the remainder of these number of real valued solutions, right? So okay, where was I? Okay, so there you go. So the number of them as a result would be what? Well, okay, so this part is your job to add up all these values. It turns out there's a much faster way to do it. Well, it turns out if you add up all these numbers, it comes out as, well, yeah, you need to do it basically. But it comes out as 2005 choose 3. And then you say, well, actually, now that I know the answer, wait a second. I think that it comes from, wait, what was this thing called? Okay, you know it. It's not Pascal's identity. This is hockey stick. Yes, hockey stick. Wait, is this hockey stick? I think it is. Yes. Oh yeah, it is hockey stick. I was thinking, okay, well, I was planning to use the other combo technique to, this is hockey stick. Indeed it is. Okay. All right, step back. Before I do that mod 1000 business, okay. So this is hockey stick. Yes. Oh my gosh. Okay, plug in 1 times 2 over 2. Well, yeah, this is hockey stick. Okay. So summation n times n plus 1 over 2 is just n plus 1 choose 2. Yes, n equals from 1 to 2003. So start plugging in. So if you plug them in, okay, so this is just starting n equals 1. So you have 2 choose 2 plus, and plug in 3 choose 2 plus wow. Okay, and then 2004 choose 2. Hey, I know you. So by hockey stick, this is just 2005 choose 3. All right, so this is pretty good. Actually, I entertained this solution, which means, and obviously you guys can easily compute this value modulo 1000, which is, so if this is equal to 1/6 of 2005 times 2004 times 2003, which you need to calculate it modulo 1000. Okay, so let me move this. So that's 1000 here. So that's a 5, that's a 4, that's a 3. Multiply them out. 60 over 6, that's a 10. Okay, so because it's an AIME question, the answer is 0, 1, 0. That's one way to solve this. Okay, I think this method is pretty good. I don't have to do anything else. But yeah, alternatively, you can use stars and stars and bars. All right, and if you wonder where are the stars, the bars are there. So we have 3 bars. The stars are what? Are the intervals. There you go. In total, we have, yeah. So in total, we have 2002 intervals. And so yeah, those are the stars. You can think of those intervals as the stars. So 2002 stars. So that's a second solution. We're done, right? And 3 bars. That's it. So that's again 2005 choose 3. That would have been a direct way to solve this. But usually, if this is the first time you're doing this, maybe the first method was more natural. I think that's pretty good. And I kind of enjoyed the ending as well. This ending followed by hockey stick identity. Hockey stick identity. One of the 3 identities that I enjoy in combo, right? So we have the Pascal identity related to combinations. We have the Pascal identity, this hockey stick identity, and do you guys remember that? What's the third one? Okay, if you know the third identity that I'm thinking of, write it on the comment section. I doubt anybody is watching the video after 34 minutes, but I mean, I just wanted to just say it anyways. All right, so I hope you guys enjoyed it, and looking forward to see you guys in our next video, which will be about 2019 Poland number 6. All right, see you guys.